Mr. Tarrou, in this lesson we're going to do 3 examples of graphing logarithmic functions using tables, and we're not going to be allowed to use our calculator. A couple of years ago, 2-3 years ago, I did a video related to the same topic. I spent a lot of time explaining the inverse relationship between exponential functions and logarithmic functions. I'll have a link to that lesson in our description. And I finished off with an example very similar to how we're going to work these problems out. But then the last 1 or 2 examples I did was just sketching these functions based off of transformations. You know, knowing the parent function and moving it left and right and up and down and flipping it and whatever. Well, if you don't know what the parent function looks like, maybe you know what y equals log base 2 of x looks like, but you know, what happens when the base is equal to 1/2? What happens when there's a leading coefficient or a plus at the end, or maybe there's so many transformations involved in the equation that your sketches of these functions based on just transformations and knowing what the log, the parent function looks like just ends up being a little bit rough. I don't want a rough sketch. I would like a really nice graph. At least know, 5 points that these go through, and find those 5 points without the aid of a calculator. And again, get that really nice accurate graph, not a rough sketch just based off of transformations. And as we finish these 3 examples, we'll talk about the domain and range of these graphs as well. We're going to put these first 2 graphs on the same XY coordinate system because I just want to point out the differences in effect when we have a base that's larger than 2 and what the logarithmic graphs look like when your base is your logarithm has a base which is between 0 and 1. We also have a vertical stretch with this a value which is greater than 3, but I really want to talk about what happens with these different bases. Remember that you cannot take the log of a negative number. I'm just sort of reviewing some logarithmic facts here for you. The answer that you get from a log is an exponent. Hopefully, if you're watching this video, you already know it. I like to mention that the common log base 10 of 100, is equal to 2 because the base of that log was 10, common log, 10 squared. I'm pointing to here like it's base 10, but if I do log base 10 of 100, we get an answer of 2. That is an exponent. It's 10 squared gets you back to 100. There's at least a 5-second review of how logarithms are related to exponents. Okay, so when you look at logarithms, when you convert from log form into exponential form, you need to remember that, of course, the base of the logarithm is going to be the base in exponential form. You do get exponents from logarithms, so we'll have, say, 2 to the y, and then, now the x plus 1 isn't an answer and as far as having this equation written in logarithmic form, but it will be the answer when you rewrite this equation in exponential form, and that's exactly how we are going to graph these 3 examples without the aid of a calculator. We're going to convert them into exponential form, build up a t-table, pick out some smart numbers so we can do it in our head, and plot those points and get our graph. Now, just one more time, if you do know your parent functions and you do know your transformations, you'll know that the difference between y equals log base 2 of x plus 1 and y equals log base 2 of just x is a horizontal shift to the left, or translation to the left, of 1 unit. So let's see what this looks like, though, doing this problem with the t-table. We have a base, we have an exponent, and we have an answer. That is, again, how we're going to do these problems without the aid of a calculator. So we have 2 to the y power is equal to x plus 1. We see that the y variable is up here in the exponent, so it's sort of like where the math is happening. And we're going to, therefore, we're not going to re-isolate this y. It already was in the first place. I guess you could make it a log base 10 or log base e, but again, I want to do this without the aid of a calculator. So I can, take the base of 2 and raise it to certain powers in my head. So we're going to solve for x, and we're going to do that by subtracting both sides by 1. And we get 2y minus 1 is equal to x. Now I said we were going to do this with tables, and normally when you do a t-table, you pick the x values, but that's because the y is normally alone, and the x is over there where the math is happening. Well, now the x is alone, And it's the y that's involved with all the math, 2 to the y power. Now there's a minus 1 with it. So when we build up our t-table, we're going to be picking values of y. Now, what values do you want to use? Pick some small numbers around the 0 range and use integers, more than likely. We want to pick some numbers that we can easily raise 2 to that power. So let's just say y is going to be -2, -1, 0, 1, and 2. I don't usually just use 2 or 3 points for graphing a function which is curving, right? What direction is it curving? How sharply is it doing that? So let's make up some, let's do some work here. So y is equal to -2. Well, that means that we're going to have 2, the base of 2, to the exponent of -2 minus 1 is equal to x. 2 to the -2 power. How do you deal with or get rid of a negative exponent? How do you rewrite this or move this base around so that exponent's going to be +2 as opposed to -2? Well, you move the base. If the base is in the numerator with a negative exponent, you drop it down. If the base is in the denominator with a negative exponent, you'll move it up to the top of the fraction. And if you understand division and the properties of exponents, you can hopefully understand how moving the base up and down will change the sign of your exponent. But this will be 1 over 2 squared minus 1. That is going to be 2 squared, of course, is 4. So now we're looking at 1/4 minus 1. When you start dealing with fractions, you should make everything look like a fraction. So we need a common denominator. We're going to multiply the numerator and denominator of this 1 by 4. So we have now 1/4 minus 4 over 4 is going to be equal to -3/4. So when we have a y value of -2, our x value is going to be -3/4. When we let our y value be -1, we're going to have, for this next line, we're going to have 2 to the -1. We're going to rewrite to get rid of the negative exponent as 1 over 2 to the first, or just 1 over 2, minus 1 over 1, because now we're going to combine these fractions, multiply the numerator and denominator by 2, giving us 1/2 minus 2 over 2. And when you have common denominators, you just add or subtract those numerators, and 1 minus 2 is equal to -1/2. Now, we're going to let y equal 0, and anything to the 0 power is going to be equal to 1, so we're looking at 1 minus 1, which is going to be equal to 0. Then we're going to let y equal 1, and this is going to go a lot quicker because we're not dealing with fractions anymore. 2 to the first is 2, minus 1 is 1. And then when we let y equal 2, I guess I could have rewrote that line as I was going, 2 squared is 4, and 4 minus 1 is equal to 3. That was pretty easy. I didn't have to require a calculator to do that. And I can't do base of 2. My calculator only does base e and base 10. Who cares? You don't even need a calculator. So let's see here. X is going to be -3/4. Each of these tick marks counts for 1. So x is going to be -3/4 and y is going to be -2. So I'm just going to try my best to estimate that. We have an x value of -1/2 and a y value of -1. We are passing through the point of 0, 0. Logarithmic functions, if there has not been a horizontal transformation, we have a plus or minus here inside the math function to move the graph to the left. If there's been no horizontal translation or transformation or slide or whatever you want to call it, log functions will always pass to the point of 1, 0. Then we have 1, 1, and we have 3, -2. Now, by definition, logarithms must have a base which is positive. If they had a base which was negative, it's nice to talk about it now that we have it in exponential form. A negative number raised to a power, again, we're talking about functions, right? Some kind of graph that would even look like a graph and pass a vertical line test. If you have a base which is negative and you raise it to an even power, the answer is going to be positive. Well, okay, forget the plus or minus something constant going on, but And then when you take a negative base, that base of the logarithm is the base of your exponent, a negative number raised to an, let's see, what did I just say? Even power is positive and an odd power is going to be negative. So if you had that negative base or a negative base in an exponential function, the graph would be oscillating back and forth, violently between positive and negative values, and you wouldn't get a smooth curve or function. So that's why your bases have to be positive. If your base of your logarithm has to be positive and what you get out of it is an exponent, so 2 to something has got to be equal to what's inside that parentheses, you're not going to take a positive number, raise it to any power. I mean, I just took, well, I raised it, but I took a positive base of 2 and raised it to the negative 2 power. I didn't get a negative answer. Well, okay, that's negative, but it's after we subtracted by 1. You're never going to take a positive base, raise it to any power, and get a negative answer. So you cannot log 0 and you cannot log a negative number. So logarithms are always going to have a vertical asymptote as part of their graph. And we can see the graph is curving down. And the first one, which I really intended on doing in yellow, is going to look like this. Instead of the vertical asymptote being at x equals 0, it's going to be at x equals -1 because of that horizontal shift to the left, which I didn't even have to think about. The table of values, you could see that developing, and our graph looks something like this. Now, it's sort of a sketch and sort of a graph. I mean, this part of the graph is really accurate, but now, I'm not sure how quickly it's going to climb as we go to the right, but it's going to look something like that. So now we've got our first graph done. Y is equal to log base 2 of x plus 1. Now, you might have thought, I know what the parent function looks like. I know it's going to move to the left anyway. But, that's not just a sketch. It's more of an actual graph. And then, do you know the parent function for a base of 1/2? And with that vertical stretch of 3? So let's do this with the t-table. And how is that base of 1/2, the base being between 0 and 1, going to compare when we had a base which was bigger than 1? Well, okay, let's just put it in exponential form. You can't put this into exponential form until you get the I want to get the logarithm function alone, have a leading coefficient of 1, and then convert it into exponential form. I could bring the 3 up as a power and say that it's log base 1/2 of x to the 3rd and then convert into exponential form, but my y is going to have some kind of exponent, my x is going to have some kind of exponent, and I want to just plug values in for y and get x, get the answer for x. I just want the x alone. So we're going to divide both sides by 3. I don't know why I picked up green when the problem is in purple, but we have y over 3 is equal to log base 1/2 of x. Now we have x is nice and alone. That's going to be handy for when we make the t-table. The leading coefficient of the logarithm is equal to 1, so we're going to go into exponential form, which is base, exponent, answer. So we have 1/2 raised to the y over 3 power is equal to x. Now you think, well, that looks a little bit nasty. But you have control when you're building a t-table of what you decide to set as your value of y. Because here y is the independent variable and x is the independent variable, at least the way the equation is structured. So when we set up our t-table, and I want to do this without the aid of a calculator, why don't you just pick values of y that you can divide by 3, like 6, 3, and 0. So we're going to have x and y is going to be -6, -3, 0, 3, and 6. And let's plug these in and find out what happens. Let's see. Let's get the negatives out of the way first. We're going to have -6. So -6 divided by 3 is going to be a power of 1/2. That's going to be 1/2 to the -2. If you want to rewrite your base so it does not have a negative exponent, you flip that base. So we're going to have 2 to the +2 power, and 2 squared is equal to 4. Repeat the process with -3. And we're going to have -3. -3 divided by -3, that's coming in here from here, right, is equal to -1. And that is going to be equal to, 2 over 1 to the first, which of course is just equal to 2. Now, when we put in that y value of 0, we're going to have letting y equal 0, we have 1/2 to the 0 over 3 power, 0 divided by 3. 0 can be on top, just can't be on the bottom. 0 divided by 3 is 0. We have 1/2 to the 0 power, which is anything to the 0 power is 1. That is true because, let's see here, how about, what is x to the third? This is just an example, a little side example. What's x to the third divided by x to the third? I mean, we know that anything divided by itself is equal to 1, right? Well, when you divide like bases, and if I didn't want to just say, oh, anything divided by itself is 1, when you divide like bases, don't you subtract the exponents? And wouldn't that be x to the 0 power because 3 minus 3 is equal to 0? Yeah. Anything to the 0 power is 1. Okay, I don't know if you knew that or not, but some of my teachers in high school used to always say, oh, it's just a rule, memorize it. We have, oops, be nice if the answer was there. So now we're going to let y equal 3. Look at that, I already got the bottom of the 3 in there. We're going to let y equal 3. 3 divided by 3 is equal to 1. And we have 1/2 to the 1 power, which of course is 1/2. And when we let y equal 6, we're going to have 6 divided by 3, which is 2. And 1/2 squared is 1/2 times 1/2. I don't know if you really need to see that expanded, but in case you do, 1 times 1 is 1. And 2 times 2 is equal to 4. All right, so let's see here. When x is equal to, we're going to do this in purple for the graph. When x is equal to 1, y is 0. I don't know why I'm doing that point first. When x is equal to 1/2, y is equal to 3. So when x is 1/2, y is equal to 3. You see how the graph's not rising up to the right? It sort of seems to be falling. When x is equal to 1/4, the y coordinate is all the way up at 6. So 1, 2, we're at 3, 4, 5, 6. When x is 2, the y value is -3. And when our x value is 4, the y coordinate is -6. So x is 4. 1, 2, 3, 4. And y is -6. So 1, 2, 3, 4, 5, 6. And that graph is going to look something like this. Well, more than something like this. Actually going through these points, but how quickly it bends over as we go to the right. I totally answered. To answer that, I'd have to make a bigger t-table. But, I said I was going to talk about domain and range. Now notice the base being between 0 and 1. This graph is falling. Let me check the time, by the way. Okay, so with that base bigger than 1, and most of the time your bases are going to be bigger than 1, those logarithms kind of come up from the bottom and go over to the right. And with that base, though, of 1/2, that is going to kind of get a function which I like to call monotonic decreasing as opposed to monotonic increasing. Yeah, it's interesting. Now, let's see here. The domain and range of this yellow graph, the domain is going to be, it goes all the way to the left and approaches -1, but x equals -1 is a vertical asymptote. So the x's that make up this graph, this yellow graph, are never going to become -1, the x values, but it will approach -1. So the domain are your x's between -1, whoops, almost we're at infinity, -1 to infinity. And the graph, as you can see, goes down, and it's sloping over sharply to the right, but it will never stop increasing. So this yellow graph is going to go up and down forever. So the range, which are the y values, are going to go from -infinity to +infinity and beyond. The purple graph, well, it goes up and down forever as well, so its range is going to be the same. Its domain, though, we have a vertical asymptote at x equals 0. So this purple graph is going to have a domain of 0 to infinity. Now I just have one more example, and really it's the same kind of deal, just a more complicated example. So I'm going to step off, put that question up here, and just reveal the solution one step at a time so that you could pause the video, try it on your own, and see if you can't get that logarithmic equation written into exponential form, and just check your work, because I'm just going to reveal the next example small steps at a time, because really the process is the same. Be right back. So we have our last example. It was y is equal to -2 plus log base 3 of x plus 4. And as you saw, trying to isolate that logarithm, we added both sides by 2, then went into exponential form, base, exponent, and answer, and then finally had to subtract both sides by 4 until we completely isolated the x. Okay, I cheated a little bit and used a calculator to figure out that 35 over 9 was 3.9, so I'd have to do the long division by hand and so on. But with the other remaining decimal, I did not really intentionally want my x values to be so close together and be at least a tiny bit difficult to graph. I just looked at the exponent of y plus 2 and thought, well, why don't I pick my y values? So the middle term is going to have an exponent of 0, and we'll have a couple of negative exponents and a couple of positive exponents, and that's how I came up with the idea of using these y values for my t-table. Also, I went ahead and before graphing or putting the vertical asymptote up on our graph, what is inside the logarithm, again, has to be positive. It has to be greater than not equal to 0. So x plus 4 is greater than 0. Subtract both sides by 4, and we got the placement of our vertical asymptote. Put the points down, and that is the end of our last example. I hope this helps. I'm Mr. True. Bam! Go do your homework. And happy Pi Day!